Hi everyone, welcome to today's lecture, which is all about multiple linear regression. Part one. Part two is coming in theaters near you. It's coming soon. This is a massive lecture. It's split up into two sections, but everything you've learned in correlations will feed into the first part of today's lecture as well, which is all about a review of correlations. So that's because it's foundational to our understanding of simple linear regression, which is very related in terms of its concepts, and then building from there to multiple linear regression analyses. So I'm excited for today's lecture, largely because once you understand the concepts for today and start applying them, you'll really be able to go through literature that uses this so commonly. I mean, many research areas, many of the research that they conduct in terms of analyses is with multiple linear regression analyses. So I think it gives you a good foundation in understanding much of the research that's out there and that's published, but also understanding its strengths and why it's used, and also what you need to look for when analyzing results from the output. So we're going to walk through lots of examples, analyzing it together step by step, so that when you either generate the outputs yourself and see what's going on, or review papers and look at what's happening there, you'll get a good sense as to how to understand that output. So that's really a key focus for today. So the purposes of correlation, it's exploration and descriptives for correlation. You explore the relationships between variables. You're trying to describe the relationships that are occurring between variables, and in some cases you're trying to explain the relationship between variables. But there's always this tension when looking at correlations, because say I'm looking at the relationship between going for a walk outside and I was going to say getting into an accident, but I don't want that to be to be something that's worries people about going outside. Let's say going outside and seeing a bird. That's a much nicer example. So we're trying to understand what the relationship is between going outside and seeing a bird, and say that's highly related. And someone may say, well, okay, maybe there's a relationship between going outside and seeing some birds, or perhaps this could be explained by the fact that the person lives in a more country environment, or an area where there's lots more birds around, and so they're more likely to see birds in that case. And so the friction that we see with correlation is that it can't necessarily account for other variables that could control for the relationships that we see. So this is where multiple linear regression has its place. It allows us to actually control for other variables. And in addition to that, it allows us to make predictions about what's going on. Factor analysis allows us to explore, describe events as well. And regression has that explanatory power as well. And we'll see the relationships already with correlation and simple linear regression. But regression does have the capability to allow for prediction. So you could say, given your health status, say your blood pressure, your fat mass, the amount you exercise, can you predict the chance of cardiac event in the next 10 years or next 5 years? So these are things that we can do using multiple linear regression analyses, particularly when you have longitudinal data. So regression can be used in cross-sectional analyses, so all data is collected at one time point is cross-sectional, and longitudinal is when data is collected at multiple time points. And so with multiple linear regression or regression analyses, you can actually, say, use the data from one time point or a few time points and predict what happens in future time points as well. So predictors collected prior to the outcome measures. So that's a longitudinal study there. So that's really a framework to give you a sense of these different tools, but keeping in mind that they're all tied through correlations. It's what underpins everything within these analyses. So what's the definition of a correlation? Hopefully this is very familiar to you. It's a linear relationship between two variables. So you're trying to see what is the relationship between those two variables. And again, flagging the technical terminology that's here in statistics, it's a language, and the more you understand the terms and connect them with their meanings, the better it will be for your understanding of these concepts that they relate to. So covariance, that was the sum of the cross products for the unstandardized covariance. Remember, that's when they're on the same measure and you're able to get a sense of what those cross products are. Correlation is the sum of the cross products, but it's standardized, right? So it gives us that standardized effect size between -1 to +1, and the sign indicates the direction, and the value indicates the size. So if it's 0.9, we know it's a highly a strong correlation. And if it's 0.01 or 0.1, we know it's much weaker correlation. We have the coefficient of determination, indicates percentage of shared variance. That should be a capital R squared there. So it's a coefficient of determination. It's the percentage of shared variance that's there. And the correlation does not necessarily equal causality, right? So correlation, what's driving there is the understanding that causal factors, you're not able to conclude causality just through correlations alone, noting that if things are causally related, they will likely be very correlated, but you can't just look at a correlation and say, oh, that's a causal relationship there. There needs to be more evidence, and maybe theoretical justification, or maybe even one variable happening for another to get a sense of causation that's occurring. So again, the shared variance, this is where you have two variables, and correlation is really an investigation of that shared variance. How much of the variance between two variables is shared. Before I say the variance one more time, we will go into variance in a moment. So linear regression is really an extension of correlation, and they're really interrelated concepts. So this is where you're predicting a dependent variable from an independent variable. As a reminder, dependent variable is your outcome measure or what you're measuring. Independent variable is what's changing. So, for example, explains and predicts an outcome, criterion variable, dependent variable. These are all the same words that are used in different contexts, but whenever you hear the word outcome or criterion or dependent, that's all related to dependent variables, based on a linear relation with a predictor or independent variable. Direction is important, unlike correlation, due to interpretation. So independent variable is used to explain the dependent variable. And when I say direction is important, I mean in the sense of when you put it into the analyses. So for a correlation, you could have variable A here, variable here, B here, and then you could also swap it around and it doesn't matter. You get the same answer, same output. But for regression, linear regression, it actually doesn't matter. You want to be saying that your independent variable is what you're changing and your dependent variable is what you're measuring, and you're actually, the direction of effect is from the changes that are occurring in the independent variable and what you're observing in the dependent variable. So for example, here, age and years of education. So age is the independent variable in this situation. Dependent variable is years of education. So the relationship may be, as people are older, they're more likely to be educated as they age. So why does it matter in terms of linear regression? Well, the reason why it matters is because foundationally and statistically, if you were to run a correlation with age and years of education, and then you run a simple linear regression with age and years of education, you'll get the same answer. But this is where the statistics blend with the theory and our interpretation. So to really understand the relationships of and possible causal effects of one variable on another, you need to understand the direction that's occurring. And then you make an argument. You say, look, for all these reasons, for maybe perhaps there's a mechanism of action that is likely to drive what you see, or some theory that drives the phenomenon that you see, we think that the changes in independent variable result in changes in the dependent variable. But it is susceptible to reverse causation, but this is where the theory comes into play, where you have to sort of get a sense as to, is there a strong rationale for the direction going from this way to that? And if so, how can you test and embed that within it? But this is why direction is important in linear regression analyses. So in here, this is response, intercept, slope, predictor, error. So these are just terms that I want you to get familiar with when it comes to a regression model. And this scary formula over here is really just giving you a sense as to what a regression looks like. So before we go into that formula, which actually maps on to the English above it, what I want to show you is a few things. One is the response is the dependent variable. That's what we have here on the y-axis. And on the x-axis, we have the predictor, which is the independent variable or the predictor variable. We have the slope, which is here. So we'll get an estimate of the slope often at times. And then we have an intercept, right? So this intercept is where this slope crosses the y-axis. So this is the intercept here. And then you have error. What is error? Error is these residuals here. So the residuals are where the circles that we see here are our actual data points, and the red line is our sort of predicted or line of best fit through the data points. And so the difference between the actual data point and what we predict is the error. And so that's what's represented here as error. And so this formula here is showing the response, the intercept, the slope, the predictor, and the error. So that is explained here in English above it. So really, these are key terms that I want you to be familiar with to get a sense of what you see and connecting it with when you see an estimate that says the estimate of the slope. What we're talking about is actually this line here, right? So that's the slope here. Okay, so what are residuals? So that is the vertical distance between the line of best fit and each observation. So this is the unexplained variance. So when we talk about unexplained variance, that's the difference between the total difference between the data point we have and the line of best fit, the residuals there. So these gray lines, well, you can think of them as all added together. So in other words, the residual term represents the difference between the score predicted by the line for participant I and the score that participant I actually obtained, right? So that is what residuals mean in the context of regression. So I'm going to come back to something that we talked about in correlations, just because you may already be sensing that it's such a critical foundational concept when it comes to understanding regressions, and that is variance, right? So I talked before about shared variance. It's relating to this. I talked about the unexplained variance that relates to this as well, right? So here is our line of best fit. This was our example where we had lecturers and we said how many friends each lecturer has. And so the first one has 1, second one has 2, third one has 3, fourth one has 3, fifth one has 4. And the line of best fit is the average line that's fitted here. And so in this case, we're just fitting the average, and we're seeing what the difference is between that average predicted value and each of the dots that we see here. And you can see that it's pretty close for some of these values, but a bit further away for other values, right? And so what I was trying to help you understand, in addition to connecting what the line and errors were with this example, was actually understanding where the term variance comes from. And so hopefully in your mind, you're always connecting variance with the concept of error. So also when we're talking about unexplained variance, you're like, oh, okay, so that's the difference between data points and the predicted line. So you're trying to get a sense of that. Or shared variance, okay, it's a sense of how they move together. Those two variables move together through the variance. And so the total error is the sum of deviances. So when we sum up all of these errors, and we get the sum of deviances. Now that equals to 0 in this case. So that's the argument as to, because we have negative values and positive values and they cancel each other out. And so that's why we square each of these values so that they all turn into positive. But then we saw that there was an issue with that, because if you square all the values and then you just have more and more values, you'll get larger and larger numbers at the end of the day. So it's dependent on how many data points you get. So we have 5 values here. If we got a 6th lecture, that would also be higher automatically just by the fact that it's a squared value. So we said, how do we account for this fact that it keeps increasing with the numbers of people that we have? So we said, well, if we divide this by the number of people that we have in our sample, or degrees of freedom, which is number of people minus 1, then we get the variance. So this is the critical point, that variance is a sense of that total error that we have around our predicted line. And so that's the calculation of how we get to the variance. So you have each of the individual participants' data point minus the average point, which is here, and we're squaring all those values so that they're all positive, and then we're dividing it by degrees of freedom. And then I showed you that there's actually a relationship between the variance and standard deviation. So standard deviation is if you square root that variance, that big sigma sign is sum, by the way, and if you square root that, you get the standard deviation. But all of this was to show that variance, standard deviation related concepts, but also the variance relates to the error. And so standard deviation is just how that the data points are distributed around the line best fit. And so least squares criterion is where the sum of the vertical deviations is, which is the residuals, is the sum of squares, and that's what I've said here. Sum of deviances is equal to sum of squares, squared errors, and the line of best fit minimizes the total sum of squares of the vertical deviations for each case. So y hat equals b times x plus a. This is where a is the point at which the line crosses the y-axis. So that's actually what, in this case, this is what a would be when x is equal to 0. So if x is equal to 0, y hat is equal to a. So a is the point at which it crosses the y-axis, and b is the slope of the line. So in this case, the slope is this line here, right? So there's no slope in this line, and this is where we have a, where it crosses the line. And just to keep that in your mind, I think it's similar here. So here it was termed as b naught, which is the intercept, but that's the same thing can be thought of as a, which is the intercept. These are different ways of, you may be asking, why are you showing me so many formulas that have different names for things? It's because there's different ways of representing it in maths, and I want to make sure that you have a sense of, foundationally, they're all showing the same thing, which is this thing here, response, right? Your dependent variable, you have your intercept, which is where it crosses the y-axis when x equals 0. You have your slope, which is how steep this red line is. You have your predictor, and then you have your error. So all of these formulas are all showing the same thing, just with different letters. And so a is where it crosses the y-axis, and in this case, b is the slope of the line. So let's talk through this example, and I'll talk about y hat a bit later in a moment. So let's talk through the example of how does the number of record or album sales rise with increasing money spent on advertisements. So which variable makes the most sense as the independent variable, and which is the dependent variable? Why I'm having you think about this is because I want you to start thinking intentionally about the design of your multiple linear regression. So it's different correlation. We're not just putting in the variables, seeing the correlation. We're actually having to think of, theoretically, what would the direction, what would make sense? So stop the video, have a sense, and then come back once you have a go at that. And so hopefully you're back, you have an answer, and that answer is, so we have album sales, so that's the number of record sales in a week after the release of the album, so that's in thousands, and then the adverts, which is the amount of money spent on advertisements in the week before the release of the album, so in thousands of dollars. And so what you're thinking about here is you have the adverts and you have album sales. You can't really control album sales, but you can control the amount that you're spending on adverts. And you can actually change that. You can change that quantity and then see what the effect of that is on the overall album sale. So through that logic, adverts would be your independent variable and album sales would be your dependent variable. And so to represent that, here is a diagram which has the amount spent on adverts as our independent variable on the x-axis and record sales on the y-axis. And so what we can see is the slope that's here. So we can see the slope, we can see where it crosses the y-axis. So these are the things to look at in our regression model. So the y-axis is somewhere between 100 and 150. And we can see all these data points. And you can see that it predicts some data points pretty well. It's the data is on it, but for many data points, it's sort of not on that line. So we have quite a lot of error here, and we can quantify that error. So the equation for linear regression, I said I'd come back to what this y hat meant. Well, in a perfect world, if you didn't have any error and you're able to perfectly predict the outcome variable here, y hat, that's the predicted values of y. Beta value is your slope, so it's the rate of predicted increase or decrease in y for each unit increase in x. So for every dollar you spent on adverts, you get an however many records sold more. And A is just the y-intercept, so the level of y when x is 0. So this is in a world where you don't have any error. This is where I would be able to say to you, hey, if you spend $100,000, you'll have this many album sales, and when you do that, that's what occurs because your model predicts the outcome perfectly. Now, this is never the case. There is always error. We've talked about error already in different contexts, measurement error, sampling errors that can be introduced. And so error is just a quantity that we try to reduce as much as possible and then explain as much as possible. And so with error, we have y, which is dependent variable value, x, which is your independent variable value, a, which is your y-intercept, so level of y when x is 0, b, which is slope of line of best fit, and then e is your error. So this is quite a common formula you'll see for fitting a linear regression line. This is the formula for a linear regression. So let's go through this example step by step. So in this example, the dependent variable was the record sales in thousands of dollars or thousands of sales, and independent variable was the amount spent on advertisements, so in thousands of dollars. And the regression coefficients, you have the beta, which is the rate of increase or decrease in record sales for each additional $1,000 spent on advertisements. And then you have A, which is the baseline record sales. So remember, this is when no money is spent on advertisements. So that's also thought of as 0. So when no money is spent on advertisements, where does the slope intersect with the y-axis there? So the explained variance, so the explained variance from the example, is the correlation between the two is 0.58. The amount of variance accounted for is 0.33, which is 33% of the variability in record sales is associated with variability in the amount spent on advertisements, and the p-value is less than 0.05. So that's the outcome from this analysis and from this figure. Here's what it looks like when you run it in R, and I want to sort of draw your attention to a few points, right? So this is the formula in the first line. So it returns from the album data set, so that's the data. And we have sales, the dependent variable, and the amount spent on advertisements is the independent variable. This is showing you the distribution of your residuals, and you want your median to be around 0 and for it to be normally distributed. If you remember our assumptions of in linear regression analyses or in correlation, is that the residuals are normally distributed. And so the coefficients here, this first one is where it crosses the y-axis when x is equal to 0. And so this is at 134, which maps on pretty closely to what we see here, 134. And the adverts here shows you how, for every dollar you spend on advertisements, how many additional album sales are sold. What I want to, we'll come back to those numbers in a moment, but what I want to pull apart here for you is showing you multiple R squared is the 33%. That's where that comes from. The 33 R squared is equal to 0.33. We'll talk about adjusted R squared a bit later. And the F statistics, we'll talk about that later as well. But I just want to orientate you with where all these numbers come from. We'll talk about F statistics now. So what is the F statistic? So the F statistic compares your model that you've developed to the baseline model. What is the baseline model? Well, the baseline model is if you were to fit the average of the dependent variable. So in this case, the average of the dependent variable is your albums, the number of albums sold. So if we were to fit the average of that, that is what we're comparing in this ANOVA. So you run an F-test, and it shows that it's significant. So the F-test says the album model that we run here, LM1, which is this one here, which is adverts and sales, is better than using just the average of sales alone, right? So that's what this significance value tells you. It compares this model to this model. This model is just album LM0 uses the mean of records, number of records sold, and this uses the actual regression line that we fit. And it says, yeah, actually it explains the variance better than the average, right? So if you go back to this line here, the F statistics 99.59 on 198 degrees of freedom, you'll see that those numbers map on very closely here. So the F statistics 99.587, 198 degrees of freedom, right? And the p-value is there as well, right? So all of that is obtained. So the model itself runs the ANOVA automatically for you, but I just wanted to pull apart to show you that you can pull that apart and understand where that comes from and what that means. So conceptually, this is what it means, right? We have the data, the amount spent on adverts in $1,000, record sales in thousands, and the first initial model uses the average of record sales, and it fits that through the data. And then the second model fits the line of best fit through our data, and it compares the two with one another. And it says, actually, yeah, this fits the data points. There's less unexplained variance here than there is here. And you can sort of see that. You can see that the line actually captures more of the data than it does here. There's a lot more dots further away from the line than here. But really, that's what that ANOVA is doing. Let's talk about the regression coefficients. So this says when $0 is spent on advertisements, 134,000 records, 134,100 records are sold, right? That plus E to plus 0.2, it just doesn't have space to put the other zero. So it's just in different notation. So move that decimal place forward 2 spots. So that's what it means. So when $0 is spent on advertisements, 134.1 thousand records are sold. So that's important. So whenever you look at a regression model and you want to get a sense of, okay, so what happens when x equals 0? What happens when there's nothing in the independent variable? What do we see in the dependent variable? If that question makes sense to ask, then this is where you'd be looking at the intercept. However, in some cases that doesn't make sense, and we'll come back to that later in the lecture. I've got an example for you. But in terms of adverts, here's an example that for every $1,000 spent on adverts, because the measurement's in thousands of dollars, an additional 0.09612 thousand albums are sold. So that's because the E to the negative 0.2 means move the decimal place back 2 spots. And then it's in thousands. I think the units are in thousands, so you move it forward 3. So you get 96.12 albums are sold for every $1,000 spent, right? So that's what those regression coefficients mean there. Now, you can also standardize your regression coefficients, but before I get into that, I'll actually talk through what the standard error and t-values mean. So the standard error really reflects the concept of, if you were to run the study over and over and over again and in different samples, what's the standard deviation of those sample means of the different samples? So say you run this study 20 times and you get different estimates. What's the standard deviation of those estimates? And that gives you the standard error. So it really reflects the precision of your estimates in relation to the true population value. So say in this example, there's a true value as to how many adverts are sold in this relation with number of records sold. Then to understand the standard error, if we were to take a whole bunch of different sampling means, we look at the standard deviation of that distribution, we get the standard error there. So it's a measure of precision, and it's actually quite closely related in terms of the estimate and the standard error to the t-value. So the t-value is your test statistic, and to calculate that, if you divide your estimate by your standard error, you get your t-value. And so to do so, the t-value is actually what you use to calculate the p-value. And that's why you see the letter T here, right? So all of these are related. And so the estimate relates to your model, and here this relates to your slope. That's the slope that we see. The standard error relates to in some ways, that the precision of that estimate to the true population. And then we have the t-value, which is really related to the estimate divided by the standard error. It gives you the t-value, and then we use that to calculate the p-value. So when we're looking at regression coefficients, you may be able to assess what it is in standard units. So I've been talking a lot in terms of unstandardized units. So I'm using the units of measurement that are available in the example. But you can also ask the question in standard units. So you may be saying, how does adverts and sales relate to one another in standardized units? So in this example, as advertising budget increases by 1 standard deviation, album sales increase by 0.57. Yeah. So in the unstandardized example, this is where you say for every $1,000 spent on adverts, we get a 96 increase in albums sold. In the standardized way, we talk in terms of standard deviation. So every 1 standard deviation increase results in a 0.57 standard deviation increase in album sales. Now, we can convert those values, right? If we know what the standard deviation of advertising budget is, that's what that standard deviation represents. So in this example, it's 485,655. So the standard deviation for album sales is the standard deviation for album sales is 80,699, but for advertising budget, it was 485,000. So this is just based on the data that's there. So this would constitute a change of 46,683. And how is that worked out? Well, it's just this standardized unit multiplied by the standard deviation of album sales. So therefore, for every 485,655 spent on advertising, an extra 46,683 albums are sold for the first week of sales. This seems like a convoluted way of explaining it in terms of, or explaining the findings. And you may be asking, why would we do it in this way? The reason we do it this way is because in some cases you may be wanting to express what the changes are in standard units. You may be saying, well, in one standard unit increase in X, we see this many standard deviation increases in Y. And then this would allow you to do that, but also convert it back. So those standard deviations just relate to the standard deviations of the measures that are being used in the regression coefficients. So let's make a prediction. What if we wanted to predict record sales? I mean, this is something that can be incredibly powerful to be able to get a sense as to what's going on. So when $100,000 is spent on advertisements, how much do I get back for this, right? So this is y hat equals b of x plus a. So y hat here is 143.74. Yeah, so that's the predicted value. And we get that with our 0.09612, right? The 0.09612 is this value here, 0.09612. So that's our estimate, that's our slope, times 100, because I'm putting $100,000 in. And I'm adding 134. Ask yourself, where did that number come from? Hopefully you remembered that is the intercept. When x equals 0, that's 134. So this is just the linear regression line, right? So you give me your money, and I say, give me $100,000, and I will be able to return to you 143.74 thousand albums sold in the first week of sales. But then when I return to you the results, I say, oh, look, We predicted in my model predicted 143,000 albums sold when you gave me $100,000. But I actually only sold 130,000 albums. I'm sorry, this was the model. This is the error in my model, and so this is the residual. So you'll notice when I modeled it here, I modeled it using y hat. I didn't add any error into this model. But in reality, we know that there is error. It's not a perfect formula. And so when we predict it, this is the error. So the error is the residual. So that's 143,740 minus 130,000, right? So this was my amazing model where I got you to invest $100,000 to see albums sold. You gave me your 100,000 and you were expecting 143,000 albums sold and change. And I said, actually, no, sorry, it's a bit less. It's 130,000 albums sold. So that is the residual part of the error that we see there. Yeah. So hopefully you're now starting to connect these concepts together in terms of error, residual, and predictions. Excellent. So what we'll do is we'll take a break there. There were a lot of concepts covered. Try to get a sense as to your understanding of residuals and that relationship with error, your understanding of variance, and getting a sense of interpreting estimates from a regression model. The key things that we're looking at in terms of the slope of the line, where it crosses the y-axis when x is equal to 0, getting a sense of how much of the variance is accounted for through R-squared metrics, also what the ANOVA relates to as well. So those are sort of the key things to pull apart when you're looking through the analyses. Saying that, let's have a break, stretch your legs, and we'll regroup in a moment.